All right, so as we look at example 9, it talks about inflation and how things cost more today or like we can buy less for the same amount of money as what we used to be able to buy for. And so it says, suppose inflation decreases the value of money by 5% each year. So in other words, it says if you have $1 this year, next year will only be worth 0.95 worth of this stuff. How much will $100 buy in 20 years? So kind of the same idea. We're still looking at that P sub 0, all of that stuff. And so this is still your time. This is my amount that I'm going to start with, but it wants to know how much that's going to be able to purchase. And so if we're looking at P sub n, if we're looking at our normal equation, this is P sub 0, and then 1 plus r raised to the n power is our normal function. In this case, we're trying to find out P sub 20, like how much we're going to have in 20 years if we start with $100. But now, because it's not an increase, it's decreasing by 5%. So instead of a plus here, we're going to have a minus because it's decreasing. And then it's still raised to whatever power. So in this case, it's 20. And when I plug it into my calculator, I'm going to do 100. And then parentheses, 1 minus 0.05. And then you're going to raise that to the 20th power. And so when we do that, it looks like we can spend, or we'd really be able to buy $35.85 worth of stuff. So our $100 today will only be worth $35.85 in 20 years, based off of the idea that it decreases 5% each year. So there's a written assignment for this module. And I don't want to do all of it, but I just want to have you think about this a little bit. For the linear function, you guys are okay. It talks about how he's either offering $1.50 per bushel picked, and so this is linear, or is saying he is going to pay 1 cent the first bushel, 3 cents for 2 bushels, 9 cents for 3 bushels, and so on, tripling for each additional bushel picked. And this one is a little bit harder as you set up. So you can come and ask me, but I just want to talk about that for just a minute. So X is going to be the number of bushels picked, and this is how much I'm going to get paid. So think about, again, this is just option B. You guys can do option A, okay? If you pick 1 bushel, it says you're going to earn 1 penny. 2 bushels, you're going to earn 3 pennies. 3 bushels, you're going to earn 9 pennies, and so forth, okay? So hopefully you kind of see that the rate of change is 3. And what I want you guys to think about is when I go to write my exponential function, so remember we've got P sub n is equal to P sub 0, 1 plus r raised to the n power is our general form. We know that we're getting paid 1 cent, and then this rate of change is 3 to the nth power. Now, we have sort of an issue, because if I put in 1 penny here, so think about this. If I put in 1 penny, then I get 3 cents. Excuse me. If I put in 2 pennies, that's still a 1. If I put in 2 pennies, if I pick 2 bushels, then I end up with 9 cents. And notice how you're off. You were supposed to get 1 cent here. You're supposed to get 3 cents here when I put in 2. But you're just 1 off. I want you to think about what can you do with this power to make it so that it's going to work out. And so that's just my little hint for the written assignment. If you get stuck and want to throw some things out, or we can discuss it, go ahead and email me, or we can do a Zoom real quick and talk about it. All right, so logistic growth. It says if a population is growing in a constrained environment with a carrying capacity K and absent constraints, your growth would exponentially grow. And we're looking at a logistic growth model because the environment can only hold so much before whatever you're looking at starts dying out. So logistic growth is always a recursive function. So this is our function or our equation, which is always that. And so as we look at it, this is always our previous value. The R is our rate, so our growth rate. The P sub n is your previous value again. K is your carrying capacity. And this is our previous value again. And we just plug it in to the formula to figure out what we're going to get. So it says there's no explicit formula for this type, which I just talked about. The growth rate is not constant. Okay, so that means that it's going to grow until it reaches that carrying capacity, and then it's going to slow down or stop or go the opposite way so that it can maintain the carrying capacity. Because what they're talking about is if let's say you have a pond and it can only hold so many fish before there's too many fish to swim in that pond and there's not enough oxygen. Or if you're looking at an area, it can only hold so many animals before there's not enough food or not enough water. And so then the weak ones start dying off. And so it kind of fluctuates a little bit where it's not staying consistently growing. Sometimes it will reduce. But the main idea is, as you're doing this problem, you're just plugging in the pieces. It's just a formula. It will be you can use your notes, like on the final, it will have that formula on it. So it's not anything you need to memorize. So this is your population, that your starting amount. It says they're introduced into a wildlife sanctuary. It says it's estimated that it can sustain up to 400 deer. That's your carrying capacity. Absent constraints means there's like not a disease that happens or a fire or something like that. And it says it grows by 60% each year. So that's my growth rate, which would be 0.6. So it wants us to plug those values into that equation. So if I do P sub 0, in order to find that, that's just what I start with. So that's 50. So that's the easy one. Actually, we can just write that. If I'm finding P sub 1, then I have to use the value from P sub 0. So previous value is 50. The growth rate is 0.6. I do 1 minus my previous value, which was 50, over the carrying capacity, which is 400, times the starting amount or the previous amount, which is 50. And I'm just going to plug that into my calculator. So, clear. So we're going to go 50, and then it's plus 0.6, and then parentheses, 1 minus 50 over 400, close your parentheses, and times it by your previous amount, which was 50. So that means that you have 76.25. If you're talking about real animals, then you would say 76, because you can't have a fourth of an animal. So you would say 76, but when you're calculating it into your calculator, you always use the decimal. So when I do P sub 2, I'm going to do the 76.25 plus 0.6, 1 minus the previous, which is 76.25 over 400 times 76.25. So basically that 50, everywhere you see the 50, it changes to 76.25 because that's the previous amount. So again, when you put that in, you're doing 76.25 plus 0.6, and then parentheses 1 minus, not 50, 1 minus 76.25 over 400, because that's your carrying capacity. Close your parentheses and then times it by 76.25. Oops, 25. So you get 113, what was it, 113.25 again. Okay, which, I mean, technically it's 113, dear, but that's the idea. And you could keep going. If I was doing P sub 3, I would do the same thing, but everywhere there was 76.25, I would put in the 113.25. But all of this would stay the same. And then you'd put the 113, this stays 400, and then you'd put the 113. Get your answer. So whatever you're trying to find. Usually they don't make you go too far because it does take a lot of time. When you're looking at example 11, same idea. It talks about lizards on an island, and the population can support 1,000 lizards. So that's our K. It says there's currently a population of 600. That's our P sub 0. And it grows by 1.5%, or 150%, which is 1.5 as your rate. And we're going to find our population in 3 years. Because it's 3 years, we have to do it a few times. So P sub 0 is 600. P sub 1 is 600. Plus your rate, which is 1.5. And then it's 1 minus 600 over 1,000 times by 600. And we just plug it into our calculator. We'll do it for P sub 2, P sub 3. And we're just going to keep putting our values in. And really, this is what we want, but I have to find the other two before I get there. So you've got 600 plus 1.5 parentheses 1 minus 600 over 1,000. And then we're going to times it by 600. And so we get 960. And then we take 960, we put it in everywhere there's 100, or 600, sorry. So this is 960 over 1,000. And this is 960. And we plug it in, and everything works out fine. So if I don't want to type all of that in again, you could just go second and enter, and then just go back, and you can just back up and change all those to 960. I don't honestly think that's that much quicker, but if you want to, you can. Yeah, that's not what I wanted to do. Delete. Yeah, that takes longer for me. So 960 plus 1.5, and then 1 minus 960 divided by 1,000. Close your parentheses, and then it's 960. And so we get 1017.6, which in the computer, you could put 1018, but I think it takes 1017.6 just fine. So this will be 1017.6 plus 1.5, 1 minus 1017.6 over 1,000 times 960. And you'll notice with this one, it's going to fluctuate down. So you've got 1017.6, and it'll be plus 1.5 parentheses 1 minus 1017 points. Oh, whoops. So 1017. Oh my gosh. Sorry, I'm struggling today. Okay, 1017.6. I'm just going to push the 0.6 plus 1.5 parentheses 1 minus 1017 0.6 divided by 1,000, close your parentheses, and then times by 1017.6. And you'll notice that it goes back down. So it reached, like it got to the carrying capacity, and then there was too many, so then a whole bunch, well, not a whole bunch, but they died. And what happens is as you keep going, it's going to go up and down until it gets pretty steady. So that's going to be 990.74. Which is really about 991. So that's what they're looking for. So as we look, gosh. Okay, so when we look at linear, the growth rate is adding or subtracting the same number. And when you look at the graph, remember that it's a line. So it's either a line that's going up or it's a line that would be going down, but it's always straight. When you look at an exponential function, it's either timesing by the same number or you're taking the percent each time. And so when you look at that, remember that's like it's going to go up or it could go down for an exponential function. When you look at logistic doesn't have, like, the growth rate is not consistent, okay? And so what happens when you look at a graph is it's going to start at a point and it's going to grow pretty quick. And then it's going to kind of do this fluctuation until it kind of evens out. Because it's like your carrying capacity, let's just say your carrying capacity is here. And so it's going to get above your carrying capacity and then it will drop down. And eventually it will start leveling out where your carrying capacity, like I said, it's going to grow and it's going to kind of fluctuate until it just levels out. And it's more linear in function because it's not going to have so much of a spread. Those are the general ideas of what the graphs would look like if you were to match them. That's pretty much all for for Module 5. If you need help, let me know. I apologize for my voice. It's trying to leave. Yeah, just make sure if you're getting stuck, let's plan a Zoom meeting or come in and get help so that we can make sure everybody's on the same page. So, all right. Thank you, guys.